Hello students, this is Professor Chalai, and in this video we're going to look at collection of gases over water. As always, you can follow along with our Chapter 9 workbook. By the end of this video, you should be able to compute the amount of gases collected over water in experimental setups. And so what do we mean by collection of gases over water? Well, here's a typical setup of how that might be done. Let's say you perform some experiment, right, in a little Erlenmeyer flask over here, and there's a gas evolution in this experiment. And so you want to, check how much gas is collected in that, um, just for stoichiometry purposes, which we'll look at in the next video. Well, one of the ways we could do that is to have this container be sealed and have a little pipe here, piped into a container that's overturned on water, so that we make sure that gas doesn't escape and it goes into the container, where we try to have this start out being a vacuum. Now, you might be thinking, okay, so all of the gases that come out of this little experiment goes into here and we can collect it, and that's the only thing that's in there. But when we do this sort of experimental setup, there's something else that we need to take into consideration. So let's think about water. Water, let's say this is liquid water, right? We have a molecule there. I'm just drawing this as a single big dot right now. They're actually weakly bonded to their neighbors. This is something we're going to learn in the next chapter when we look at intermolecular forces, right? But all the water molecules are sort of weakly bonded to each other, and that's why, they're held together as a liquid. However, sometimes some of these water molecules are able to break these bonds, these intermolecular forces that hold them together, and they escape into the gas phase. Doesn't matter what temperature this is, this happens at pretty much all temperatures, right? Not a lot, just a few gas molecules, water molecules are able to escape from the liquid to the gas phase, right? And so now because we have a gas water molecules up here, they will have a partial pressure, the partial pressure of water. Eventually, if this pressure gets too much, right, then you could have gas molecules sort of losing energy and falling back into the liquid phase. So this is happening all the time. Some gas molecules escape, become gas. So from the surface, they escape, they become gas molecules. Some water molecules that's already in a gas phase fall back into liquid, and this sort of exchange is happening all the time. Eventually, the rate at which that exchange happens is equalized, right? And again, we'll talk about a little bit more about that in the next chapter. But the partial pressure then of that vapor, the water vapor over the water, is what we call the vapor pressure, right? That's the equilibrium pressure of a gas over whatever liquid it's in. I show you an example here of water, how that might happen, but it can happen for any liquid. And so in here, apart from having the gas that you collected from the experiment, because it's water here, you can also expect some gases in there as well. And so there will be a partial pressure from water, and there will be a partial pressure from the gas you collected in the experiment. So as you're thinking, this is another example of partial pressures, gases with partial pressures or mixtures of gases. You could either have two different gases in there, water and whatever is from the experiment. You could have three, but water is always one of the gases in here. So the vapor pressure, as we just discussed, will be the partial pressure of a gas above its liquid phase. Now, the partial pressure depends on the temperature, right? So the more temperature you add, or rather, the higher the temperature is, the more water molecules will have enough energy to escape into the gas phase. And so the pressure would become larger. The partial pressure of water, the higher would become higher, the larger the temperature is. Eventually, at 100 degrees Celsius, the partial pressure will be the same as the pressure of the atmosphere, 760 millimeters of mercury. And that means that, well, water starts to boil at that point. All of the water starts to vaporize into its gas phase. So here, this table here just gives you the partial pressure of water at various temperatures. So if I have an experimental setup at, let's say, 50 degrees Celsius, the partial pressure of water at that temperature will be 92.5. This is all in millimeters of mercury, right? So when you're thinking of collecting gases over water, there's always going to be the gas you're thinking about and water. So let me just write that down. So the total pressure of any setup that you have like this would always have the partial pressure of water, and you need to figure out at what temperature. So at what temp? Because we just look at those values could vary depending on the temperature you're looking at, plus the partial pressure of the other gases. Okay, let's look at a question as an example. If you think you can handle it on your own, please go ahead and do so. It's nothing more than what we've been doing before. It's a mixture of gases problem, where one of the gases is water and the other is what we're interested in. Okay, so number 25 talks about determining the rate of photosynthesis by emitting oxygen in some reaction, and then they collect the oxygen gas over water. Kind of like here, you have the plant doing photosynthesis, and here they collect the oxygen gas over water. Okay, let's see what happens. The temperature is 293 kelvins, right? That's right there. The total pressure is 755.2 millimeters of mercury. Right away, you should be thinking that total pressure is the oxygen gas that's emitted plus water, because it's collected over water, right? Over some time period, they tell us the volume of gas that was collected, 1.02 liters. And they want to know what's the mass of oxygen. Okay, so this is the total pressure. We know the temperature, the volume. We need to find the mass. Now we know that there's also a partial pressure of water in this experiment, so all we need to do is figure out what the partial pressure of water is at this temperature. If we convert this to degrees Celsius, which is what this table is written in, just to make you do some more temperature conversions, this is 20 degrees Celsius, right? So I would just write here, where it's 20 degrees Celsius, this is also 293 Kelvin, so that we can find it easier later. Okay, at 20 degrees Celsius, this is the partial pressure of water, 17.5. So partial pressure of water, 17.5 millimeters of mercury, which means that the partial pressure of oxygen is the total pressure, 755.2 minus the partial pressure of water, right? And this gives us, I believe, well, let me see, because I converted all to atmospheres, which we need to do anyway, but this gives us 755.2 minus 17.5 gives me 737.7 millimeters of mercury. But let's just convert this to atmospheres, because that's the units we need to use anyway. You could have converted this to atmospheres up here, but all of these values that I give you here is in millimeters of mercury, just because I want you to do even more conversions. But if I divide that, I get 0.9707 for sig figs atmospheres. Okay, so that's my partial pressure of oxygen. Now we know that the partial pressure of a gas times the volume is equal to the number of moles of that gas times R times T. Right? We don't need to know number of moles, we want to know mass, but we need to find number of moles first. So number of moles of oxygen will be partial pressure of oxygen times volume divided by R times T. We just plug numbers in. Lots of numbers to plug in, 0.9707 atmospheres. Volume was 1.02 liters. R is always 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature was 293 Kelvin. So that means that we got what? Atmospheres cancel, liters cancel, kelvins cancel, mole is what's left over, which makes sense. We're finding number of moles of oxygen, and that comes out to 0.0412 moles. Okay, we're not done though, right? Because we want to find mass. But that's a thing. That's a conversion that we know how to do since we've been doing it since chapter 1, I want to say. Mass of oxygen, we number of moles, right? Times the molar mass of oxygen, O2, is the formula. So the molar mass of oxygen is 16 times 2, which is 32.00 grams per mole. Moles cancel out, and the mass of oxygen I get as 1.32 grams. Okay, I would like you to try number 30 on your own. Same idea, you're collecting gas over water, so your total pressure should be whatever gas you're collecting and water. Okay, let's look at number 30. So we're making hydrogen gas by reacting a metal like zinc and hydrochloric acid. You react to produce gas. In case you're wondering, this is what happens. So zinc, solid, plus hydrochloric acid, gas, right? I'm balancing it as I go. You produce H2 gas plus Zn2 plus and Cl2. I think that's aqueous. And that's how you produce hydrogen gas. That's the equation. Okay. So you're reacting this to produce gas, and then you're collecting it over water. But as we all know, if we're collecting it over water, it means that we also have partial pressure of oxygen. So our volume, it tells us that we collect 154.4 mils. We need it in liters, so that's just 1.1544 liters. We have a pressure, a total pressure of 742 millimeters of mercury. And we have a temperature of 25 degrees Celsius, but really that's 298 Kelvin. So 25 degrees is 298 kelvins. We go up here. Let me just put this 298 kelvin, so I makes it easier for the future. The partial pressure of water is 23.8 millimeters of mercury. So the partial pressure of water at that temperature is 28. I already forgot. 23.8. See, I forgot. Okay, 23.8 millimeters of mercury, which means that we can find the partial pressure of the gas that we are interested in, H2, will be the total pressure, 742, minus 23.8 millimeters of mercury. But I want to convert that to atmospheres, so let's do that at the same time. I get 742 minus 23.8 divided by 760, I get 0.945 atmospheres. Okay, so that's a partial pressure. They're asking for the mass of hydrogen. So same thing, we need to find number of moles first. So let me see, what's a good color? Blue. Number of moles of hydrogen, which I'm going to use the same equation that I used above. It's the partial pressure of the hydrogen times the volume of hydrogen divided by the ideal gas constant times the temperature. So the partial pressure of hydrogen we just calculated as 0.945 atmospheres. The volume we got as 0.1544 liters. Ideal gas constant 0.08206 liters times atmospheres divided by moles times Kelvin. And our temperature is 298 Kelvin. There we go. Cancel, 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 cancel. We're left with what is that? Punch all that in your calculator. I believe it's 0.00597 moles. We're not done though. It's asking for mass. So that's easy. Mass of hydrogen is number of moles of hydrogen times the molar mass of hydrogen. Hydrogen is 1.01 multiplied by 2. That's 2.02 grams per mole. And so that I get a mass, so this is the molar mass of hydrogen, H2, right? That's the formula for hydrogen gas. I get 0.0121, whoa, what just happened? 121 grams. Okay, so that brings me to the end of collecting gases over water. The only thing to remember here, or the most important thing to remember, is whenever you do have an experimental setup like this, whatever gas you're collecting, always remember there's another gas in there, water. And that gas has a partial pressure, and I give you a whole table over here of what the partial pressure of water would be at various, or rather the vapor pressure of water at various temperatures. Okay, in our next section, we're going to go over how we can use gases in stoichiometry. Remember, stoichiometry is looking at chemical reactions and trying to balance things on the left side and the right hand side. So we're going to see how gases work in chemical stoichiometry. I'll see you in the next video. Bye.